Alrighty, so I was getting ready, putting everything together to come today, and I was getting my collared shirt on. I was like, wait a minute, I got that shirt that's got the roasted out ammeter on it. That's the one I got to wear today. So that's why I'm wearing this shirt. But so we're going to talk about meter movements. I did 2 videos. You'll notice numbers 235 and 236 that talk about just your basic analog panel meter movements, what they are, how to use them, how they work, and how to repurpose them if you want to use them for another purpose, regardless of what the scale says on it. So they are on my channel. Like I said, if you haven't subscribed, please do. Thanks to Bob kind of urging me on to kind of get subscribers. I'm now up to about 70,000 subscribers on my channel. So, and thank you. So almost 8.5 million views on about 265 videos starting about 5 years ago. So it's but it's a lot of fun, and it's for getting responses like this is why I keep doing them. So, but anyway, those 2 videos are there. Really easy to find my channel, W2AEW on YouTube. You find it. So, all right. So let's talk a little bit about meter movements. So this is what we're going to kind of talk about today. Just a little bit of an introduction to what these meter movements are, how they work. Very brief history, 1 page. Okay, on history here. I'll get corrected probably on some of the dates because I probably don't have them right. But, and then we're going to talk mainly about a movement called the D'Arsonval movement. That's kind of the most popular analog meter movement there are. There are a couple of others I got a 1 page on we'll talk about. Then we'll talk about how the meter works, and then how, if you're going to use, put one in a project that you're building, how you check it out, make sure it works. And then once you know that it works, how you get the parameters out of that meter, so understand how to repurpose it and change it into a voltmeter or an ammeter of your desired, for your desired purposes. So that's what we're going to talk about. So very brief history, 1 slide here. So kind of the early meter movements were called galvanometers, and they were named after Luigi Galvani, who kind of discovered that if he passed a current through a dead frog's leg, it twitched. So just in honor of that, I guess, I don't know, they named these meter movements galvanometers, and that was in the late 1700s. I'm sorry? Okay. So 1820, Ørsted noticed that a compass needle moved when a wire passing current was nearby, and that kind of led to these compass tangent galvanometers we were talking about earlier. Think about how you had to calibrate these things. It was basically a compass that got aligned with the Earth's field, and then the coil of wire would actually change and work against the Earth's magnetic field to move the needle around. Very nonlinear, but this was what there was in the early 1800s. This Jacques Arsène D'Arsonval kind of invented this moving coil meter movement that we're going to talk about mainly today. Stationary magnet, coil of wire that actually will move around with a needle attached that's kind of on a couple of bearings and suspended by kind of a radial spring. So we'll talk a little bit about what they look like, and I'll pass some things around here as well. So let's take a look at what we're looking at here. So it's called a moving coil meter movement because the coil that actually creates the magnetic field that causes the meter move, it actually moves along with the pointer. There are some other meter movements that don't have a moving coil. So let's look at the anatomy of that. Okay, so there's the permanent magnet that's in these things is a big C-shaped magnet. It's actually a really powerful magnet, and then so that is kind of broken. The C is kind of broken here and here. It's kind of cut away here, so you can kind of see what's going on. This is the moving coil that we're talking about with the meter attached to it or the needle attached to it. There's a couple of coil springs at either side here. These are very, very fine little phosphobrons or whatever they are, kind of springs that are on there to kind of work against the magnetic field to kind of so that the meter as it moves around for a given current, is kind of working against those springs. There's a couple of bearings. Sometimes they're little jewels at either end to kind of suspend that whole thing. As you might imagine, it's all pretty delicate. Okay, and that's what you'll find. If you find one that's broken, you're better off leaving it alone unless if you like working on watches or something like that, then you probably would enjoy working on these meter movements. But they'd be kind of tough to kind of get working again if they're broken. If there's something bad with the coil or something, just forget about it. So how does it work? It really just works by current passing through this coil. So it really kind of passes through this top spring into the coil, around the coil, and out the bottom spring and out the other wire. Okay, and that that coil sets up a magnetic field that works against the magnetic field that is set up by the permanent magnet. So it's kind of like a motor that never turns more than 90 degrees or so. So as the more current that flows through, the more that magnetic field is going to oppose the permanent magnet's magnetic field and start to rotate around. The only thing that restricts it is the spring. So the more force you apply, the more it kind of pushes against that spring. And that's kind of how those meter movements work. Okay. But again, pretty delicate stuff. But what I'm going to do is I'm going to pass one around here. Just hang on a second. Let me put this mic down. Just for a sec, this is the guts of an old Simpson 260. Unfortunately, I hate to see the guts of one because I love these meters. I've got a couple that work. This one, unfortunately, didn't. Someone had roasted it. So what I did is I'm going to pull the meter movement out of this and pass it around so you kind of see how these things are made. See all the structure that's in it. But what you'll see, actually it looks like I'm missing a screw in here, but that's fine. So what you'll see in the back here, this is the big magnet here. And you can see the scale is kind of moving around on me here. So I'm wondering if it's going to survive the trip around the room here, but let's see.
Moving scale.
It's a moving scale, moving meter. But if you look really carefully, you'll see the coil, you'll see the springs. There's actually a little zeroing a lever kind of down at the bottom that is used to zero the meter out. Usually if you look at an analog meter, it's got a tiny little screw at the base of the meter. That's to kind of set the preload on the spring to make the meter sit at zero. Okay, but I'll pass this around because it is kind of roasted, but just try to keep it intact as it goes around the room, but I want everybody to kind of see what they look like. There were two screws holding the scale on, so the one was probably buried inside this housing somewhere now, but so just be a little bit careful as you bring it around so everybody gets to see it before it completely falls apart. So but you can pass that around, take a look at it. But you kind of see how that matches up with the diagram that we have up here in terms of what these meters look like internally. So how do these things work? Well, they all respond to current. So you'd say, well, I've got a voltmeter. Why does it respond to current? Regardless of what that scale says, the meter itself, the analog meter itself, responds to current. Okay, whether it's a voltmeter, a power meter, an ammeter, an ohm meter, the meter itself is responding to current. It's what you do around that meter that turns it into a voltmeter or an ohm meter or a power meter or whatever it might be. Okay. One of the things I'm going to talk about here as we go on is something called full-scale deflection, or I'll abbreviate it FSD. And what we're going to talk about mainly is what current does it take for that meter to go from zero all the way to full scale. That's one important parameter we're going to need to know if we want to repurpose the meter and use it for something else. So we're going to talk about full-scale deflection, the amount of current that it takes, and what voltage drop appears across the meter terminals when you're at full-scale deflection. Okay, because these meters all vary. Now, as you might imagine, the coil itself is not zero resistance. It's going to have some resistance. And what you'll find is that the lower the full-scale deflection current, like 50 microamps, the coil resistance is probably going to be in the order of a few kiloohms. Okay, but then other meters that have got a full-scale deflection of a couple of hundred microamps or a milliamp or 10 milliamps, the coil resistance of those is going to be much lower. Okay, typically these meters are going to have just a couple of hundred millivolts across the terminals at full-scale deflection. So Ohm's Law will kind of tell us what all the other parameters are, but we'll go through that in a little bit more detail. But I just wanted to give you kind of an order of magnitude of what we're talking about here in terms of full-scale current and what that means in terms of the coil resistance and the amount of voltage dropped across those terminals. Okay. So how do we turn it into a voltmeter? Well, we turn these meters into a voltmeter by simply putting a resistor in series. Your old analog multimeters will have a switch, for the different ranges, and all you're doing is switching in different values of what we call a multiplier resistor, which is going to in turn limit the current through that meter. The larger the resistor, the higher the voltage scale is going to be on the meter. Pretty simple. We're going to go through the exercise of what you do to compute that. So if you've got an analog power meter you're building into a piece of equipment and you want it to respond to a certain voltage, how do we do that? We'll talk about how to do that. Now the meter itself is going to have a full-scale deflection current, but let's say I want to have a different range for current. So if you're going to do that, you're going to typically then put another resistor in parallel with the meter itself. Okay, So that what that'll do is that as current comes in, some of that current will go through the shunt and not go through the meter at all, and the rest of it will go through the meter. Okay? So if you want to have, if you've got a 50 microamp meter that you want to respond to 1 amp full scale instead of 50 microamps full scale, you'd have to set up a shunt resistor that carries the bulk of the current away from the meter, and then the meter will respond to just a smaller portion. And again, I'll show you the exercise of how you compute that new value if you want to repurpose a meter and give you a higher range for that. Okay. Some of the other types of meters that you'll find out in the wild that aren't quite as popular. One is an iron vein movement meter. Okay. And this like all meters, they respond to the repulsion of like magnetic fields. Okay. It still responds to current. This particular type will respond to both AC or DC. Most of the ones that I've seen have been higher values of full-scale deflection, like on the order of, 100 milliamp, 10 milliamp, 100 milliamp, things like that. Not as popular as the NJARC valve. I don't know all the details about why that is, but that's just the case. The iron vein movements aren't as popular. And there's another one, an electrodynamometer, like the NJARC valve movement, has a moving coil, but it doesn't use a permanent magnet. It uses an electromagnet. Everything's kind of all in series here. And I've come to learn that these are mainly used in power meters. Okay, but it's just another type that's out there, but you're likely not to find them in the wild and on a Hamfest table or something like that, or a flea market table. But those, I just want to mention those because you might see them in the wild. But what do they all have in common? They all respond to current. Okay, so they all respond to current. They're all going to work the same way when it comes to understanding what the parameters are and how to repurpose them and use them for something else. All right, so if we want to repurpose an analog meter, what do? Okay, well, obviously I picked up a meter, now I want to make sure it works and that kind of a thing. Oh, do you want to check that out? Am I just holding it?
No, it must be a bit more.
Okay. No, we'll try it again. Okay. So if you're going to pick up, you see these meters out on the flea market tables, and if you want to use them, you got to check it out and be sure it works. There's actually a couple of things you can do before you even leave the table, and before you lay your money down. So we'll talk about that. Now, most meters are going to be kind of like the one that's going around, and like some of these other ones here. Like here's another one to pass around that is intact. You probably won't break this one. I'll pass that one around too. Most of them do not have a built-in series resistor to set a voltage scale, or a built-in shunt resistor to set a certain ammeter scale. Some do, and you got to really look at them carefully to see, but you almost have to kind of test them sometime to be sure. But regardless of what the scale says on it, it probably won't have those things in there. I've actually got an example here I'll pass around. This one, if you look carefully through the clear black plastic, you'll actually see a pair of resistors in there. And there's actually 3 terminals on the back of this one. This is actually calibrated as a voltmeter with the resistors already in there. I'll pass this one around. If you look really carefully underneath the tiny piece of circuit board, you'll see a couple of resistors in there. But that's a bit more the exception rather than the norm. But you can take a look and see what that looks like as well. But again, most of them are not going to have them in there. Even if the meter says it's 100 volts full scale, it probably doesn't have the meter in it. Oh, was that the end of the Simpson meter? So, all right. Simpson made stuff to last, so it's good. So, right. Okay, so first thing you want to ask if you find a meter on a table somewhere, is that meter any good? Okay.
Depends if you drop it or not.
Well, that's true. So if it's a meter, if you look at it and you take a look at the scale on it, if the needle itself is bent, you can be pretty sure it was abused either mechanically or electrically. You could put enough voltage on a meter to slam the meter off to one side and actually physically bend the meter. So if it looks bent or it rattles, okay, or something like that, it's probably not worth picking up unless it's really interesting looking to you. And again, you like working on delicate things because they're very difficult to repair. But so bent, or if the meter is stuck, like it's stuck in one spot, it doesn't move. These are the kind of things that you might want to think twice about, unless you really like the look of it. The next thing you can do is do the rock and shake test. Just rock the meter back and forth. Okay? If you rock the meter back and forth, does it move freely? Or does it get stuck in one spot in its arc? Okay? And you can kind of play around a little bit and move that meter around just to see. And does it return to 0 each time? If it returns to 0 up first, do it again and again. Does it return to 0 again? That will kind of tell you whether it's kind of free or it binds up somewhere, okay? Another trick that you can do is the short and shake. If you short the two terminals together, remember it's kind of like a motor. So if you short the terminals of a DC motor, what happens? It resists that movement. So if you look at it carefully, how much does it move when you're rocking it? Carry yourself a little alligator clip lead and clip the terminals together and rock it again the same amount. Some meters will be very, very slight, but it'll be slightly more damped in terms of how much it moves. And that'll kind of tell you, well, the coil's good. But I would say that some meters are pretty sensitive to that. Some of them are not at all. So I wouldn't call that as a completely go, no-go test. I've got a couple that I shorted them out and they look almost exactly the same, but they still work fine. So I would call that as just something else you can try. Make it look like you know what you're doing. And then when you offer the guy 50 cents for it, he's not going to argue with you, right? So I would do that. So if it kind of looks like it moves okay and that kind of thing, now we want to go and characterize that meter, take it back home, and now go look at it and see how can I repurpose it. In order to repurpose it, we need to learn a bit more about the parameters of the meter. What is its full scale current? Okay, what's the voltage across the terminals at full scale deflection? Okay, so how do we do that? So again, I talked about this full scale deflection parameters, and there's really just three, right? It's just Ohms Law. At the end of the day, from an electrical standpoint, the meter just looks like a small resistor. Okay, because we're not going to talk about the AC properties of it, because typically we're looking at DC applications for this. So what we want to determine is the current at full scale, we'll call that IFSD, the terminal voltage of the meter at full scale deflection, we'll call that VFSD, and of course, you can calculate the resistance of the coil with simple Ohms Law. Okay, but all you really need is the voltage and current at full scale. Once you know those things, then you can go off and try to repurpose the meter. Okay. But I always say tread with caution. They're really easy to damage when you're doing the testing of these things. So I want to measure what this is. If you put too much current through them, too much voltage across the terminals, you kind of, oops. It doesn't take much of an oops to really damage these things. You'll notice for the meters that go around, especially that Simpson one, that the wires in that coil are really, really fine wires. Okay, that might be designed for a couple of hundred microamps, right? If you throw a half an amp through it, you'll probably cook it. Okay, that's what happened to that one. Okay, that meter, somebody put too much current through that meter movement, and I forget what it was supposed to be, a 50 microamp movement or something like that, and it took about 200 microamps to get full scale on that meter. So that's why. So someone shorted some of the turns together by putting too much current through it. Okay, really easy to damage. And that's why I put some of these pictures up here, because you can see there's hundreds of turns of wire on these things. Okay, and it's really fine wire, hundreds of turns of wire that are a space of about 1/8 of an inch, if that. So, okay, so be really careful when you start to go and measure these things. So how do we actually measure these parameters? Now here's the simple setup, and I'll actually go demonstrate this here. Okay, we want to measure the full scale current and the full scale voltage. Now ideally you want a variable power supply. Okay, if you don't have that, you can get away with a battery or a fixed power supply and use a variable resistor, okay, instead. And then either a selection of fixed resistors or maybe a fixed resistor in series with a potentiometer or a trimmer, to kind of limit the current through these things for you to make your measurements. And then you need at least one known good meter, a DMM, a digital multimeter, an analog meter, whatever it might be. You need at least one. 2 is better, because we really need to measure 2 parameters, right? We want to measure the current, we want to measure the voltage across the terminals. And the setup is actually pretty simple. We're going to come out of the power supply, go through one of the meters to measure current, all right, and then go through a series resistor element. And I'd recommend starting with something like 100K, because a lot of these meter movements are going to be like 50 microamp, 100 microamp, 200 microamp full scale. So 100K resistor will give me 100 microamps at 10 volts, right, if there was nothing else in series with it. So it's a good place to start. If you've got a meter set up and you're making some adjustments and your power supply doesn't go up high enough, then turn it down. Throw another 100K resistor in parallel with that one, or pull it out and put a 10K resistor in there, whatever you need to, but work your way up to it. Don't start with a 1K resistor in here and say, well, let me go see. And you turn your power supply up to a half volt and ping, and you ping the meter. Okay, it's a good way to kind of bend a meter movement or something like that. So start high and work your way down. Again, you could put a pot in series with this. If you're going to use a pot and a fixed power supply, I'd recommend still using a relatively large resistor because you don't know, well, let's say, is the pot all the way up or is it all the way down? If you start the wrong way, you'll find out pretty quick, what happened, okay? And again, so if we're measuring the current or measuring the voltage across the terminals, if you don't have 2 meters, you can get away with one and just make one measurement at a time, okay? The first thing you want to do is validate the polarity of the meter. Now, most of them, when you look at them, most of the ones I've seen, when you're looking at the background, the positive terminals on this side, the negative terminals on that side. But it's not always the case. So you want to validate that first. So what you do is dial your power supply down to 0 or dial your pot all the way up to maximum, okay? And then turn it on, right? Look at the meter as you adjust just a little bit of the power supply. And if it looks like the meter's going the other way, stop, right? Reverse your connections on the meter, and then you can go ahead. Okay, just don't whack it too hard into the stop going the other way either. Just as much damage going that way. So once you got the polarity validated, then you just very carefully adjust either the power supply or the pot until the meter reads full scale. And once it's at full scale, now I can actually go read the full scale current. Because this is a series circuit, so the current everywhere in the circuit is the same. Right, so regardless of what my burden voltage is for the ammeter or anything like that, I'm going to have the same current flowing through the meter as I have everywhere else. So now I can directly read that full-scale current. Okay, if you've got a second meter, then you can put that one right across your meter here and measure the full-scale voltage across the terminals of the meter itself. Now, of course, the digital multimeters are nice because they got a really high input impedance, or you got your nice vacuum tube voltmeter, really high input impedance. But even your analog meter should have a high enough input impedance to work it. But some of them are 1,000 or 2,000 ohms per volt. That really won't be enough. You really want something that's got more than that in terms of a peak. So it doesn't really appear as like a shunt resistor in parallel to that. But so a digital multimeter would be best to do that with. And again, you can kind of do these one at a time if you've only got 1 meter. Now, a couple of options too is that some people, myself included up until recently, I didn't really have a good DMM or a DMM that would measure these really small currents very accurately. If I had the Bird watt meters have got a 30 microwatt meter movement, and I didn't have meters that could read that really accurately. So another way to do it is, well, just don't use the meter like that. So basically short this right to the resistor, adjust things for full scale, then measure the voltage across this resistor. And you know the resistor value, so you can calculate the current that way. So if you don't have a really good ammeter, you can kind of get away with measuring full-scale current by just measuring this voltage, which will be a lot larger than that one, and that's a known resistance. So now you know what the current is. So there's a couple of ways to kind of get around that, okay? And again, you can measure one thing at a time if you've only got 1 meter to work with, okay? And once you know these two properties, the full-scale voltage and the full-scale current, now I can go and change the scale on them. I can repurpose the meter and use it for something else. So if we want to change the full-scale voltage of a meter, or, so like this meter says it's a 5-volt full scale, but the meter itself is probably a 100 microwatt movement or something. So it isn't really a voltmeter per se until you put a resistor in series with it. So it's quite simple to say. We add a series resistor, we'll call it R sub S. The reality is, though, is that R sub S will oftentimes, it's there to limit that current, but it'll be very rare that the value you need to reach a particular voltage is probably not going to be a standard value that you got in your box. So usually you got a fixed resistor followed by a trim pot of some sort. Okay. So let me give you a little bit of a tip on how to kind of pick what those values should be to kind of get started. Okay. Actually, before we do that, I've got a little demo here to kind of show how to measure those parameters that we were just talking about. So let me switch over to the camera here. Just give me a second. Let's see. Okay, so let's see if I move this out of the way. Let's see if this is still moving. Hold on a minute. All right. Might have to close and restart this app, but let's see. Yeah, we're frozen. So let's close this app and restart it. And boom. Now I'm going to pull this back over there so you can see it. There we go. All right. So there's my setup. Remember we talked about we're going to come out of my power supply here. The positive lead of the power supply is going into the ammeter. That's the meter down on the bottom here. We're coming out of the ammeter and going to one end. Oh, 100K resistor. You're going to watch me set this stuff up back live again, so hang on a second. Okay. Okay, so I got one end going to this 100K resistor. The other end of the 100K resistor is now going to the positive terminal on the meter. Okay. The negative terminal of the meter returns back to the negative of the power supply. So if we scoot back actually to, so now I've got the things hooked up. My other two leads here are going to be my digital multimeter, which is the one on the side here. Let me hook that up. Okay. So now the top meter here is going to measure the terminal voltage across the meter. This is measuring current through. We've got the power supply turned on. So now as I turn the power supply up, we're getting some deflection, so I've got the polarity there going the right way. So now we can just turn the power supply up until I get to full scale. And right about there. And we can see if we look at the meter, we're running at, that's 100 microamps. This is a 100 microamp full scale meter. The voltage across that meter, just under 400 millivolts, 392 millivolts. So now I know that the parameters that I need if I want to repurpose this meter to something else. That's how that works. Okay. All right. So let's actually say if I want to repurpose this, what do I actually do? Again, I said RS is really going to be a fixed resistor plus a little bit of a tweak, a trim pot. Okay. So I kind of put that in here physically to kind of show you that it's really a trimmer. Could be a control, but a trimmer is often what you'll use. Now remember, this is a series circuit, so no matter where we are in this circuit, we have the same current. So that makes it real easy to compute some of these parameters. I know we're going to get a little bit of math here, but don't get scared by it. Okay. So since it's a series circuit, we're going to say that the desired voltage that I want, like if I want a certain full-scale voltage, applied to these terminals here to result in full-scale deflection, that's really just the sum of the voltages around this loop. Okay. So it's the sum of the voltage drop across my resistor and my trimmer. Okay, and that's just Ohm's Law, right? That's full-scale current times the sum of those resistors. Okay, so that's that term right there. Plus the voltage across the meter at full scale. We just measured that, so we know what that is. So that's a pretty simple equation, right? So it's full-scale voltage plus the product of full-scale current times that resistor value. Now, what we want to know is the resistor value. So all we do is just rearrange that equation. If we rearrange the equation, we can very easily calculate RS by taking the desired voltage. Okay, let's say it was for this meter that we're playing with, say I wanted 10 volts. Okay, 10 volts to subtract off the full-scale terminal voltage of the meter, 400 millivolts, say, okay, so 9.6 volts is what I want. Okay, 9.6 volts divided by the full-scale current of 100 microamps, that's 96 k ohms. Okay, so if I make a sum of 96 k ohms here, that will turn this thing into a 10 volt voltmeter. Okay, pretty simple. So what are some of the practical design tips here? Well, the first thing, calculate RS. We just did that. But now I need to put a trimmer in there, and 96K is not a standard value, so what do? What you do is you round down to the next nearest standard value. Okay, so 96K, the next standard value, like in a 10% scale, is a 91K resistor. So we use 91K, now we need about 5K to go on top of that. So what we'll do is we'll pick a pot that is twice that difference. Okay, so if I needed 5K, let's pick a 10K pot. So what that means, when I have the trimmer right in the middle of the scale, that'll be kind of about ideally where you want to be. That gives you the most room to move it back and forth to kind of take up for calibration. Okay, so that's kind of a good way to kind of pick that. All right, so that's a simple way to do it. How you just adjust to turn this thing into a different range for the voltmeter. Okay, and actually I've got that right here. I actually got lucky. I got a 91K resistor and a 4.7K resistor, so that's only 300 ohms off of being perfect. And if we stick this guy in here, this guy in series. Okay, so now, if I adjust this thing to 10 volts on my power supply, you'll see I'm sitting right at full scale here if I switch over to the app so you can actually see that. Okay, hold on. Here we go. So you can't quite see the meter that's on my power supply is sitting right at 10 volts, and now we're sitting right at full scale here at 10 volts. So I turned this meter now into a 10 volt voltmeter. Okay, just got lucky with the resistor values that I had. Okay. So how do we change the full scale current? Okay. Well, one thing that we'll tell you is that you can only increase full scale current. Right? The meter movement itself is a 50 microwatt meter movement. I can't turn it into a 25 microwatt meter movement at full scale. We can only make it a higher value. If you want to make it some lower value, you'd have to add some active electronics to amplify current to get up to that level. Just by simply putting some passive components around, you can only make the current, full-scale current larger. And it's simply done by putting a shunt resistor in place. Now, they're usually very, very small values. And just real quickly, we'll just run through the calculation here. But this is schematically what it looks like. We're going to have the desired full-scale current coming in, and that's going to split between two paths. Now, we know at the full-scale deflection, we know what that voltage is. So if we know what that voltage is, we know what the voltage is across the shunt resistor, right? We know the current going in here, because we know the full-scale current. So that means the current that's flowing down here is just that one minus that one, right? Because it's going to split and then come back together over here, right? So the current is the desired current divided by FSD. The shunt resistor we don't know, but we know the voltage across it. So simple Ohms Law, we can calculate the shunt resistor very easily. Okay, very simple calculation. Now, these shunt resistors are typically pretty small values, especially if you get up to higher values of current. So you get a meter that's designed for 10 amps full scale or something like that, or 20 amps full scale. These shunt resistors might be in the milliohms, okay, of values. And they're typically these kind of, blocks with, kind of calibrated values. In fact, if we look at the shell of this Simpson 260, and I can pass this around too, you'll notice a heavy wire running from this terminal over here all the way across. And then partway through there's a bolt that's attached to that. There was a wire attached to it. That's actually the shunt for the 10 amp voltage, or 10 inch current range. And in manufacturing, when they built this thing, they would slide that back and forth along the shunt wire until they had the right amount of shunt resistance to get 10 amps. Because, like I said, it just winds up being just, again, a couple of milliohms of resistance, because we're shunting most of that current around the meter. So you can kind of see what that looks like. Pass that around. Okay. I'm sorry? Yeah, right. So there was a lot of things wrong with that meter. So, but that's how you change. I'm not going to go through the exercise here, but that's kind of what you go through. And what I found when I've changed some of these is oftentimes you don't have resistors that small in your kit. So sometimes just the length of wire, works well. But the problem sometimes is that measuring, resistances that are that low is pretty difficult to do too. So oftentimes ideally what you'd use is a meter like this that has got a 4-wire measurement technique. I got another video on that. We won't get into that now. But there's other ways to do it, but they're sometimes pretty tough to kind of calculate. But oftentimes it's best to kind of just do it experimentally. Use a long length of wire. You're not getting the value you want at full scale. Just keep cutting it back until you get there. Okay. So once I've changed the scales for the meter, either changed it to a new current scale, voltage scale, or whatever I'm using it for, again, it may not match the display that's on the meter anymore. Okay. So what do you do about that? Well, the good thing is that for a lot of the meters, you can actually change it. I mean, you can see the Simpson meter was going around almost changed itself, and the panel almost came off. But a lot of these meters you can actually take apart. So the trick is, how do you get them apart? You'll see. I'll pass this one around too, but please don't open it. But you can. If you look on the back, it's just a clamshell of plastic that snaps together. And if you're careful, you can unsnap it and open it up. And once you do that, you'll get something that looks like the Simpson meter scale that went around. And oftentimes that scale, the metal plate that is painted and printed with the scale on it, is removable. Sometimes a pair of screws, you can pull it out. Sometimes you can't, but oftentimes you can actually get to it. So first thing you want to do is kind of get the meter apart. Some of them will have little screws that'll come apart. Some of them, let me pass that one around too. Some of them, like this one here, I'll pass this one around too. You look at this one, there's no way of getting this one apart. It looks like the metal bezel was put on here and swaged around the metal housing of the meter, so there's no getting this one apart. So this one actually says right on it, full scale 1 milliamp, so I know what it is. But you can only use the scales that are on it because you really can't get this one apart, at least I can't. Someone good with metalwork could probably cut this off on a lathe and put something together and make it work, but I'll pass that one around too. Okay. So you want to disassemble or open the meter. Do this in a very, very clean area. Really clean, especially clean of metal shavings and things like that. Because that C-shaped magnet that's in there is really powerful. Like if there's a metal shaving in the next county, sometimes it feels like it'll kind of get attracted in there. And the clearances between that moving coil and the cylinder are really, really tight. It doesn't take much buildup of debris to start binding that meter up. And because that magnet is so powerful, it's very, very tough to clean them out. So if you're going to play with these things and go inside and fix them or change the scale on them, do it in a really clean area. Okay. So again, sometimes there's screws to take them apart, sometimes you just pry them apart to get them open. And then you want to try to remove the scale if you can. Like I said, some of them will have little screws. You can actually pull the scale off, and it's usually like a metal plate that is printed. If you can't, then you might have to actually do something by slipping something underneath, making a new label that slips and adheres on top of the scale. Just do it underneath the needle, very, very carefully. But a lot of them will actually come apart, so you can do something with it. Okay. And again, you might have to keep that scale in place and do it that way. So then you say, well, while you're working on the scale, cover the meter back up again so nothing gets in there. Again, I can't stress that part of it enough because they are really, really tough to clean if something gets in there. So then you can prepare and adhere a new scale. Well, how do you do that? I found this really neat program. I'll just give you the link to it here. It's TON Software. They make it's tonsoftware.com/meter. And they actually got a really nice tool. You can actually put the dimensions of the scale that you have, what you want it to look like, what numbers you want there, what other labels you want on it, what the physical size of it all is, and it will print a really nice copy of the scale for you. Now, if you do that on a piece of like an adhesive label or something like that, you can glue that right down on top or adhere that right down on top of the plate, slip it back in there, and you're good to go. Okay. And of course, if you're good with other graphics tools on the computer and things like that, you can do whatever you want to create a new scale. Okay, it can be whatever you want. There's a really good application note on this website also that kind of describes the process in a lot more detail than I do here on one slide. Okay, but that's a really nice way to go. I've actually built some pieces of equipment with meters, and I haven't gone through the process of creating one of these new scales yet. I mean, a lot of times it's like magic marker on the glass. It's like, oh, that's the scale. I've got a meter that I use to measure the ESR of capacitors, and I just little tick marks on the thing. I know what it is. No one else is going to have to read it, but I know what it is. So, but I'll do that. But one of these days, I'll pull that thing apart and put a new scale on it. And I'll probably use this tool. Okay. Lots and lots of tutorials available online to go, more so than what we covered in this short talk today. Those first two are just the ones that I did that talk about the basics of these analog meter movements, what they are, a lot of what we just did here today. And then I also go through an example of actually calculating out what shunt value you need, putting that together, measuring that, sticking that on there and verifying that it works. So that's what I do with most of my videos. I try to mix some practical and some theory all together in the videos.
Excuse me, Alan, that's 235 and 236.
235 and 236, yep. So. But so they're not, if you just start at the top and scroll down, they're not too far down because it's, I did them, about a year ago. Okay, so I'm up at like 265 now, so. But there's others out there. This post-apocalyptic inventor, he's got a pretty busy channel that he's done some videos on that. There's a couple of others out there. If you just search analog panel meters, you'll find dozens and dozens of other videos. I can't comment on the quality of all of them, but there's a lot of stuff out there, okay? But they're really nice to kind of go play with, and like I said, I always like the look of these analog meter movements. I sat down in front of my bench where I have all my test equipment one day, and I counted up the number of analog meter movements that I could see. Whether it was on a radio or a piece of equipment or an actual meter or a distortion meter or an RF power meter, things like that. And it was like 17 or 18 analog panel meter movements that I could see. It's like, I like analog panel meter movements, so I think it's, and to me, I use them a lot, especially for when you guys are restoring a radio, you're doing an alignment. It's a whole lot easier to watch a meter move up and down when you're trying to peak an IF stage or something like that than to watch numbers on a DMM, right? A lot of the DMMs have got the little digitized bar graph, but that doesn't give you enough granularity to really kind of peak something up. So I use my analog map. I got a couple of Simpson 260s I use all the time. Okay, and certainly it's much nicer to kind of see and watch a peak or watch a dip or something like that if you're trying to use a meter. So anyway, that's what I've got. You have any questions at all? Please let me know. Yeah.
I told a couple of people about this. I have a TV7 DD2 tester.
Okay.
It uses a...
I'm not going to pretend I know what that is, but that's okay.
Well, it's a military one, right? It's a military tube tester. They want TV7 A, B, C, and D.
Okay.
And most of them use the same meters. Famistron or Famistron.
Okay.
And the range is 0 to 200 microamps.
Mm-hmm.
And the meter started going, it was sticking,
Mm-hmm.
it worked well, and then the other day it just died.
Okay.
And I actually, looked at the output, so the tube test was working fine, it was just the meter had gone.
Right.
Went on the web, guy came out with a digital replacement for the
Okay.
meter. It's beautiful.
Yeah.
It's cheap.
Yeah.
And the beauty of it is you can read the numbers rather than having to sort of interpolate
Yeah.
between.
Okay.
So, but the thing is that most of us guys, we don't like to, mess up a beautiful
Right. Sure.
piece of equipment that had an analog.
Yeah.
So I found from Korea, they
Mm-hmm.
were selling exact replacements.
Really? Oh.
South Korea.
Yeah, South
North Korean ones that love.
North Korea is still using those tube testers.
Right.
They were delivered by missile.
Yes.
But anyway, it's a lot of money, it's $60.
Okay.
But when you think about a $400 tube tester,
Yeah.
it was really worth it. But I am going to, I'll get to the bottom line in a minute. I am going to do the digital one too.
Right.
Just to have a backup.
Yeah.
So, but the thing is, he calculated the internal resistance of the meter.
Okay.
Got it, and he did a great job. And when Alan Douglas was still alive, who wrote a book on tube testers,
Mm-hmm.
he commented, because you're only 10 ohms off.
Oh, really? Oh, wow.
Yeah.
Good.
He recalculated the form, and he said that doesn't matter. He says leave it. It's
Yeah.
fine the way you got it.
Yeah.
Does it have to be that critical?
Well, to think about it, because it depends on what the meter is actually measuring and how it's calibrated. Because if the meter is measuring a voltage,
It's actually measuring current
okay,
in microamps,
yeah,
and the scale is 0 to 120.
okay. So, but if the meter movement is something less, and that the current is it's got a full scale deflection of 120 or whatever it is,
120, right.
that may not be the full scale deflection of the meter itself. There may be a shunt there.
No,
Okay.
I sort of try to look as closely as.
Okay, I mean, you got the schematic, you can certainly tell.
Yeah, when he talks about the
Yeah.
article, he says there's no shunt.
Okay, so because a lot of those meters will have different functions depending on what you're testing on the tube tester, right?
Right.
So some of those other scales might be counting on what that coil resistance is. Like if one of those scales is measuring voltage, for example, then the current that flows there.
Seriously, it only measures.
Okay, if that's all it is, then you're okay.
Yeah. So even if you're off by, I think the internal resistance is quite high.
Yeah.
It's about 1,900. Quite.
Yeah, it could be like that. Like this meter movement here. That's got about a 4,000 ohm coil resistance
so it's
on
up
that.
there.
So, yeah.
But Alan said that even if you're off by 10 ohms, it's not going to make that.
Yeah, if it's 10 ohms out of a couple of K ohms, it's under 1%, you're probably
the
fine.
bottom line is the guy took his meter that went dead on
Mhm.
and he hit it with 400 volts
Okay.
and it welded the coil back again and he was able to use it for like 4 or 5 more months.
Yeah, I think you get away with that, you know. One person out of 100 might get away with that. I mean, so just because, you know, because more likely you're going to open that wire, not weld it back together again.
Well, I guess he was
Or you're going to slam that meter somewhere, unless you physically, mechanically held the movement so it wouldn't, you know, ram itself into the wall. You know,
These
so.
orders where I hit it with
Yeah.
400 volts. and
Okay.
welded, and the
I guess if the
worked.
meter is toast and you want to try it, it just might be more toast when you're done.
Oh, really?
So, yeah, so I'd be a little bit hesitant. In your case, if you got a meter movement that's just sticking, and maybe debris or something like that in those bearings.
That's
that
probably what that was.
Yeah.
Well, now it's totally, I mean, now
Yeah.
it's completely gone. It doesn't move at all.
Doesn't move at all. Is it not? The thing is, does it not move? Like if you took the tester and you jog it, does the meter still
Oh.
stay stuck, or does it actually physically move?
It's hard to tell. I
Yeah.
can get the meter to move,
Yeah.
but it doesn't, it used to like stick a little bit about mid-scale.
Yeah.
But if you tapped it a little, oh no, if you held it vertically, if you
Yeah.
held it didn't stick.
Okay,
Held
so
it
it's probably something in the bearings, and it could be
is,
that. And think if you look at these things, and you saw that Simpson one that was going around, it didn't take much force at all to move that meter
And
movement.
you know how that happened? Some guy came over and tried to use it.
Yeah.
I was watching him, and he put he set it up wrong,
Mhm.
and when he put the,
Slam the meter over,
Slam
and
the
that
meter
that
over.
jogs everything
and
over.
ever
Yeah,
since then, it was,
yeah. I said they are pretty easy to damage that
they
way.
are,
So,
you gotta
yeah.
be, that's why I always tell people that use two testers 2 or 3 times, go over all your settings,
Yeah,
because you're gonna kill that, and those meters are hard to find.
sure.
But generally, what do you think about, using analog? You know, they're all out
Yeah,
there.
yeah,
They're easy to use. You can
Mhm.
slap an analog. They're easier to read.
yeah.
Uh,
Yeah, it all comes down to
Or is it
what
just-
are you using it for? If you're looking to kind of gauge a magnitude or peak something or look see how fast something moves and that kind of a thing, rather than absolute, digits of precision.
and-
Right? If you don't need the digits of precision, I like the analog meter movement. I think it gives you a more, better feel for what's going on.
Plus, they look nicer on a 1930s repro
Right.
transmitter. You're not gonna.
Right.
You're not gonna put a.
Yeah, what you got to do is get the guy to make, one of these, put an organic LED display on it that has an analog, a simulated analog meter movement on it or something like that, right? So, but then you get the best of both worlds. Yeah. I'm sorry.
Yeah, when they usually specify the accuracy of the meter,
Yep.
they say full scale.
Yeah.
How much does that degrade at less than full scale?
Well, the way to read that is, let's say you've got a meter that says, it's 1 volt full scale and 5% accuracy at full scale deflection. So what that means, if I've got 1 volt and 5% accuracy, it could be up like plus or minus 5 millivolts off. At 10% scale, it could still be plus or minus 5% off. Of 5 milliamps or 5 millivolts off. So that error applies across the whole scale, but the error is the least at full scale. But that error could be much larger because the amount of error doesn't really change much across the scale. So when you're using analog meter movements, you always want to try to use them so that the meter is close to full scale. It's going to give you the highest most accurate readings, relatively speaking. Make sense?
Yeah.
Was there another question? Yeah.
You mentioned the analog versus digital
Mm-hmm.
debate. I work in a vocational high school.
Okay.
I've gotten into this fight with other staff members.
Sure.
I am not a teacher.
Okay.
Just support staff. I get called to fix things, and first thing I do is I have the yellow bag 260 that I would use.
Right.
I had people, are you still using that junk for? We have all these brand new fluke meters. And
Yeah.
I have that. I said, this is faster. So they had about 6 years ago. School competes in a robotics competition. We had one of our robots in competition. I'm there with them.
Mm-hmm.
Another team has a robot that's going haywire.
Okay.
And I'm looking at it and I'm saying, I think it's a switch that so we're helping them out.
Yeah.
And they've got this digital meter and they're just trying to find this switch that's chattering.
Yeah, right.
And that's not going to work. And it's like, oh, I can see this here. And get that out of here. So I take the little yellow bag and
Yeah.
I take it out. And I'm like, that thing's ancient.
Yeah.
I hooked it up and there's the meter.
And the meter's
I said,
jogging
every time
around.
the thing gets here, the meter's still doing this. I said, now there's your problem.
Yeah.
I said, it's easy to find. I said, and it's like I tell them, so they got to learn to walk
Yeah.
before they can run.
Yeah.
But what a difference.
Oh yeah, absolutely. Well, it kind of reminds me of, I used to own a British sports car. And everybody knows British sports cars. You know about the Lucas Electric, and we used to say the three positions of a Lucas switch were off, dim, and flicker, right? So, right, so Prince of Dark is exactly right. So, yeah.
Maybe a little off topic. I asked a question about the digital meters.
Yep.
I was involved in a discussion the other day, and people were talking about how, we all have a dozen of these Harbor Freight.
Yeah, the ones they gave away for free when you bought a roll of tape or something. Yeah.
These little digital meters are typically rated for like 700 volts or whatever, maximum, whatever it is. And a couple of people were saying, yeah, but they burn up. I burn those meters up all the time now. Not from overvoltage, from running it under 700 volts in.
Yeah.
They say that these meters just don't last. Now, I have never toasted a meter.
Right.
What is it about a cheap Chinese meter?
These cheap meters that are rated to 1,000 volts or 700 volts and things like that. It really comes down to a lot of it comes down to the robustness of the design. If you look at like a reputable brand like a Fluke or something like that, these things are built like a brick shithouse. They're very very robust. Where the connections are made for the banana plugs that go in. There'll usually be reinforced connections. There'll be isolation cuts made in the circuit board to prevent arcing. All these types of things to make the meter last long, so you can plug and unplug the probes to it, 5,000 times, and it'll work just as good as it did the day you got it. These cheap meters, if you look at them and you open them up, a lot of times the contacts that are made for where the probe goes, are just bent pieces of metal that are soldered onto the circuit board with no kind of strain relief. And you use the meter 100 times, it's fine, but you got to eventually stress and fail those joints, and then they'll do things like arc, and they'll become intermittent and things like that. So a lot of times it comes down to the design fundamentally works, but it's whether you're going to use it 100 times or 1,000 times or 10,000 times, how's it going to hold up? And even things like the switch design, to switch the different modes. The good meters will generally have a real good mechanical, switch, multiple leaf contacts type of thing. The cheap meters will be a piece of metal stuck in the end of plastic that's riding across circuit board traces that can corrode. It's those types of things that can lead to problems. And where guys say that these meters burn up, the meter's probably sitting in a toolbox in the garage. The circuit boards are starting to corrode. The traces on the board are starting to corrode because they're just bare copper. They didn't do anything to treat them. And then, so the contacts on the switch start to get a little intermittent. So you pass current through them, they heat up, they burn up, things like that. So, but kept in your lab drawer, using it, a couple of times a year, it's probably going to be fine. But it's not going to hold up like, the brand, what you pay money for. So.
I tell you, the Harbor Freight meters, I have Fluke meters too.
Yeah.
They're surprisingly accurate.
Yeah, accuracy-wise and things like that, they're actually pretty good. But are they going to hold up 10 years from now or something? I got Fluke, DMMs that are 20 years old that have been bounced around and they work fine. And I doubt that the Harbor Freight one that I have would.
That's a true thing.
Right. So. Yeah.
Can you go over for the audience ohms per volt on a multimeter?
Okay, sure.
So everybody understand that.
Yeah.
I actually had that on an interview test.
Okay.
I was interviewing for a job at LabVolt.
Yeah.
I actually put that down as one of the questions.
Okay.
I came back and the guy who was my interviewer just said, "You were the only one that got it right."
Well, let's go back to my slide here because that would probably be the easiest thing to talk about. Let's kind of go back to the slide that kind of talks about that a little bit. This one. Yeah, this one here. So what's ohms per volt? You see that on the analog meter movements. What does that mean? Well, remember, we're putting these resistors in series with that meter to create, some full-scale voltage. I want a 100-volt scale, a 25-volt scale, a 50-volt scale, things like that. So the way to think about that is that if I've got this set to, let's say I had a meter that was rated at 20,000 ohms per volt, okay, and I set it on a 10-volt scale, and that's going to basically mean that the resistance going through the multiplier resistor and the meter is going to be 10 times that 20,000 ohms per volt, right? Because I got 20,000 ohms per volt times 20 volts or 10 volts or whatever that number is for full scale. That tells you essentially how much resistance that meter is going to present to your circuit when you connect it up. So when you go down to lower scales, like a 1 volt scale, then if it's a 20,000 ohm per volt meter, it looks like a 20 k ohm resistor. Okay, but at a 10 volt scale, it looks like a 200 k ohm resistor. Okay, at a 100 volt scale, it looks like a 2 meg ohm resistor. The resistance of the meter, when you put it on your circuit, is going to depend on where that scale is. The digital multimeters are typically all 10 megohms, and that's it, it's fixed, okay? But the analog meters, when they say a meter is more sensitive, like a 50,000 ohms per volt meter is more sensitive, because that means that the meter movement doesn't need as much current to go full scale. So you put a larger resistor in series, that means it's going to present a larger resistance to the circuit that you're testing, and therefore load it down less. So a 50,000 ohm per volt meter is better than a 20,000 or 1,000 ohm per volt meter. Make sense?
You get a more accurate reading.
The ohms per volt
Yeah.
is misleading.
It is misleading.
That phrase.
It is misleading because I think
It's a constant, it doesn't vary.
it's a constant.
Yeah.
It's not something that,
Yeah.
well, if I'm measuring 1.5 volts or I'm measuring 2 volts, if you're on the same scale, it's still the same resistance. The resistance doesn't change depending on the voltage that you're measuring. So you're right, it is misleading.
What's not constant is the perturbation to the item you're measuring.
Right. Yeah, so,
Distort your measurement at the low voltage scale.
Yep.
Because the ohms per volt may be constant, but the overall impedance the meter has to the circuit of the test
that's correct. Yep.
will be more perturbing in the low scale than the high
Right.
scale. And that's when you go for your vacuum 2-volt meter.
And it's a bit of a trade-off because if I say, well, I want to load my circuit less, so I'll go to a higher scale so I have a higher resistance, now you're on the lower end of the scale where the accuracy is worse, right? So these are things you have to understand when you're using these things. So yeah, you got to.
So could you back up 2 slides, I think,
Okay.
if diagram of your meter? Yeah, that one there.
Yeah.
So this is a question about the linearity of it.
Yeah.
And so just the orientation of the moving coil relative to when it's at 0 and when it's at full scale.
Yeah.
So the question is where, so it's really, my question has to do with how linear are these?
Well, they're actually pretty good, and that was part. If you look at the design of this is such that the gap between the coil and the edge of the magnet and the cylinder is consistent through the rotation.
So that's bringing the magnetic field is always coming in radially.
Yeah.
Okay.
So it's designed to kind of be linear that way. You're still going to have some nonlinearities due to Hooke's law and the spring, right? So it's not going to be perfectly linear, but they're a whole lot more linear than like the tangent galvanometer type of things are, right? These are actually really pretty quite linear. And if you look at the scales of most analog meters, you know, if you look at like a 50-volt scale, 25 is dead straight up, right? So, but they are actually pretty linear. The only scale that is typically nonlinear on these analog multimeters is the resistance scale. So, yeah.
Sometimes that ohms per volt gets pretty critical. I used to work in a nuclear power plant. One of the major manufacturers of transmitters was a company called Rosemont.
Okay.
I think they're still around. And the typical range, it was, the loop range was 4 to 20 milliamps, 1 to 5 volts. And at the beginning of when Rosemont started building a lot of transmitters and people started calibrating them,
Mm-hmm.
a lot of the plants started using really good fluke meters
Yeah.
to do the calibration.
Right.
And they started to see that they weren't working right.
Okay.
They were off by quite a bit because, I mean, sometimes you need a lot of accuracy on those things.
Yeah.
When you're only talking about a 1 to 5 and 4 to 20 loop.
Okay.
And they, you know, Rosemont finally came back and said, you gotta use the Simpson.
Yeah, because they're relying on what the load was of that meter to be
That's
part
right.
of the measurement, right?
And
So,
from there on in all the instructions for calibrating
yeah,
those transmitters,
had to use that meter. Yeah.
how to use the
Well,
Simpson.
it's funny because I did a video about a year and a half ago on transistor current sources and how they can be used as high impedance loads in circuits and amplifiers and things like that. And I actually forgot or didn't take into account the loading of the meter, and I was using, because I had a bunch of meters measuring all these various parameters of this current source, and one of the things I was trying to measure was the output impedance of the current source. And I was using it, to measure the terminal voltage by Simpson 260. And I just didn't think about, the loading that I was doing. And it wasn't until after I had the video up and I posted it, I'm like, when that output impedance was a lot lower than I thought it would be, and then I started thinking, I was like, oh, dummy, I used the analog multimeter, and that load resistance was in parallel with a very high impedance current source. So I quickly posted a video the next day. Did anybody catch my mistake in my previous video? This is what I did, and here's what it was. Yeah.
The other thing about the Simpson is that the mirror scale
Yeah.
used to avoid parallax when trying to make an accurate measurement is not just a mirror scale, it's a front surface mirror scale.
Yeah,
And that makes a big difference if you're using a Simpson 260 out the
Yeah.
big wide one.
Yeah.
And you want to get a decent accurate measurement.
Yeah.
That's a front surface mirror scale,
Mhm.
which is better than just a mirror.
yeah, but only the 260s from like Series 6 and on had the mirror scale. I've got a couple of earlier ones like that was going around that didn't have it.
We got
Yeah,
trained to use in high school, it's
Yeah.
just, there's a parallax.
yeah. So you look at it over here, you look at it over there, it's different. Yeah,
Yeah, and
Yep.
having a front surface is the best kind of mirror for
Yep.
that purpose,
Yep.
because it's under glass.
It's a good point. Yeah,
Touching briefly on AC meters,
yeah.
some of them have linear and those have nonlinear scales.
Okay.
The nonlinear ones, are they like the moving vein type?
They might be. I'm not really sure. I don't know enough about them. I mean, I've seen some like expanded scale AC voltmeters like that'll read from 100 to 140 volts. So you get a nice expanded scale around 120. There's some extra electronics to do that. The other ones that are nonlinear, they might be, like a moving vein type meter or that electrodynamometer.
You have a rectifier, so
You have a moving vein.
Well, some of them, the moving vein and the electrodynamometer don't. They actually will respond to
Yeah,
AC.
yeah.
So, but I don't know how linear they are, and that might be the case. So.
That's why I was working on a radio a while ago, and they gave a reading on the grid.
Mhm.
It said 0 volts.
Okay.
Wait a minute. But then you read the diagram, that's from 1935,
Yeah.
and they're using a 1,000 ohm per volt meter.
Right.
You measure that with a VTVM,
Right.
and you get the right grid voltage.
Right.
But, so they're not giving you the actual operating voltage,
Yeah.
they're giving you what you should be
What,
looking
what
for.
you'd see with the equipment that you use in the day, right? So it's the same thing, especially like the AGC lines on the the 5-tube radio. That's a very, very high impedance line. You got to measure that, and
Yeah,
the meters will drag it off, right?
In the better sets, where you
Yeah.
have the pin voltages in a table,
Yeah.
you usually find some fine print that tells you what kind of meter they use.
Yeah.
That's why 0 volts.
Yeah, like I said, many times, like you said, the meter will make a difference because it becomes becomes a part of the circuit because the load is not insignificant. So.
You guys inspected the 2.5 volt on this 260? Yeah, here we go again with the moving scale.
Moving scale.
You'll notice that this is
Moving scale meter.
rearranged, not linear. Because if you line up 1 volt versus the 250 volt DC, and the pointer's up on it,
Yeah.
they don't line up.
They don't line up.
Because the rectifier type actually has.
For the AC, yeah,
Yeah.
yeah,
You mentioned the mirror scales on the 260.
yeah.
As far as I know, the first 260 to have a mirror scale was a Series 8.
Oh, it might be. Well, I think.
But here's
Yeah.
the
Yeah.
hint to that.
Yeah.
Years ago, Simpson made a 270,
Okay.
which was, I think, I forget what the percentage
Yeah.
error is on a 260,
Right.
but it was tighter on a 270.
Yeah.
And 270 always had a mirror scale.
Yeah.
Because I actually
Yeah, 'cause I-
have a 270 from like the 60s.
Yeah, I've got a Series 6, and the Series 6 is the one that had the reverse banana plug.
7. No, 6.
Was that the
still
7 that had that?
regular
Okay, so maybe it's a 7 that I have that
Yeah,
has that.
maybe
then.
it's 7 starts. but
7
the
might
6
be,
is
yeah.
definitely
Inside out banana plugs?
Okay. I'm sorry?
Inside out banana plugs?
Yeah, they're inside out banana
Yeah,
plugs.
They do that for Bell system.
Yeah.
Bell system.
Yeah.
And you know what, I might have to correct myself, it may not have been the 260, it may have been the Simpson 269.
Okay.
It's got a
The big scale, yeah. The 260s are, yeah,
269, it's got a big scale.
yeah, yeah. Right.
Yeah, very, very,
Yeah. All right. Any other questions?
Yeah, do you cover in your website anything with doing null measurements? Where you can get a next order of accuracy? In other words.
I've got one video that touches on that because I did a quick little vintage tech look back on a fluke differential voltmeter.
Yeah.
Okay. So, from 1964 or something like that, and how you can use that with the null to get down to, on a 10 volt scale, get to like 10 microvolt precision with an analog meter using null measurements by precision voltage reference, precision dividers, and null that out. So I do have that one video. If you do go to my channel and search for a fluke differential voltmeter, you'll see that. So, which I used it for the video, and it's back on the shelf, and I haven't used it since. So yeah.
Where do you get your material? Where do you get the ideas to come to make a video? And I guess I'll stop you there.
Yeah.
Would you take suggestions?
Absolutely. So so a lot of times I'll get ideas for something I find interesting. Okay, something that I might get a comment on a video saying, "Hey, what about this?" or ask me a question and says, "That would be an interesting video." And I've actually got a book at home that I write potential topics in, and it's probably got 100 different topics in it that eventually I'll go through and like, oh, well, maybe I'll do one on that. So I definitely do take suggestions. If it's something that I'm equipped to do, then I'll consider doing it. If it's something I find interesting, then it boils closer to the top of the list. There's a lot of topics that I've got in there that, yeah, I should do that, but it doesn't look like that much fun, so I don't do them. But most of them come from either suggestions or questions, or people ask me things, or even from my professional career, people will ask a certain question. I had a question from a customer a couple of months ago about quadrature modulators used in RF and things like that. And he had some questions about some measurements on a quadrature modulator, measurements of distortion and quadrature error and things like that. It's like, well, that would be a good video. So I did a video on that. It's a little bit beyond the kind of some of the basic videos that I do, but I kind of cover the gamut, what I do, and that was a pretty popular video. So it really comes down to, questions that I get sometimes, or, I just did a couple of videos on using a vector network analyzer, and now I've got about 30 people ask me to do videos on the Smith chart. So I'm putting together some plans for doing videos on Smith charts. So that's kind of where they come from. So, yeah, suggestions. If it's on, hey, can you do a video on that? And I'll certainly consider it.
And I don't know if you've done restoration of things.
The only one that I've done, I bought about 2 years ago. I bought a Drake 2B communications receiver, and I did a minor resto. I wouldn't call it a restoration. It was more of a resuscitation. There was somebody on those radios, if you move the dial lamps are just like clipped onto the chassis, like little metal clips. And if they happen to move and short against the chassis, it shorts out like the heater lines of everything, of the whole heater string. So it melted the wire in the chassis. So I fixed that, and then I just did a little minor cleanup, realignment, recap. But that was the only really kind of restoration or resurrection video that I've done. I don't do them like Bob does with that nice transoceanic series that you did.
You started with a real nice piece, though.
Yes, yeah.
I saw the radio. It's beautiful.
Yeah.
Hey, could you comment on the mechanical quality of suppose you pick up a meter.
Yeah.
The arsenal.
Okay.
You don't know what's in it.
Right.
Look at it, whatever. Can you comment on the quality of what that movement is like?
Yeah, so oftentimes,
without the electrical testing.
Yeah, without just the quality. Some of these I passed around, they've got some heft, some weight to them. I found that those that are heavy, got a good solid heavy meter or a heavy magnet in them, they tend to be the more robust meters. There's some really lightweight plastic ones. So you want to kind of look inside. How much of it is metal? How much of it is plastic? Those bearings, are they kind of supported by plastic structures? I mean, they're going to be insulated structures, because they got to be insulated from the magnet, but are they more phenolic type of things, or cheap little injected molded plastic or something like that? But, it's almost like anything else that you pick up and just look at. You can kind of get a feel for, the quality of something.
You can get a clue from the brand name.
Yeah, a Weston or a Simpson or something like that are going to be good meters where it doesn't have a brand name on it at all. Then you got to.
There's a follow-up question.
Yeah.
If you pick up a watch and you see, gee whiz, I'm going to buy this watch.
Yeah.
And try to put it on, it doesn't keep time. It
Yeah.
doesn't want to stay wound. It doesn't want to work.
Right.
Whatever it is, it's losing 12 seconds a day, so at the end of a week,
Right.
maybe you lost a minute.
Right.
Big deal. But you pick up a meter and you're walking through a swap meet
Yeah.
somewhere, you're picking up something and you say, gee whiz, oh, it looks good.
Yeah.
How do you know what that balance is like?
Mm-hmm. It is hard to tell. Okay, it is hard to tell. And you have to remember, even if a meter says it's rated for 100 or 200 microamp full scale, they're not going to be exact, which is why there's always a little bit of a trimming involved. They're never a very precise, exactly 200 microamps. So.
You've got two springs.
Yeah.
Don't they have to be balanced?
Well, and they do. Well, there is a couple of measures of balance. In fact, if you look at this here, you'll see there's actually a little counterweight here. It's actually called a balance. And some of them actually have weights that go off on either side. Okay? And the idea with the balance is that the meter, when it lays down flat or when it's up straight, should read the same. And that's part of what you can actually adjust some of these weights to actually make that happen. But again, I'm not a watchmaker. I wouldn't even touch that to do something with that. But
Just at 90 degrees, work the vertical.
yeah. If you rotate them around, yeah.
The needle has to stay simple.
Right. Yeah. Actually, that's actually corrected me, and that's actually right. In the vertical position, if you rotate it 90 and rotate it back, that's what those balances are going to do. Not this way, but rotating it that way. That's right. So, yeah.
Yeah, it's funny. I have a variac on my bench for years. It's an ICO variac. made by ICO.
Yeah,
What I like about them is they have the voltmeter and the ammeter in the same box.
yep,
It's a very convenient setup.
sure,
So one day, they use these little Emeco panel meters, they're
Okay.
cheap, right? One day, the voltmeter started reading about 25 volts off. And it was annoying me. I knew where it was. But
Yeah.
it was why.
right,
So I decided to take the meter apart.
okay,
And you would be very surprised to know that what did they use inside this meter? They used 2 carbon resistors. 2 stupid carbon resistors inside the
Yeah.
meter housing.
to set the scale,
Silver tolerance carbon resistors,
yeah,
which it drifted. And,
Right.
I cut them out and I replaced them with new, I put, I think,
metal films or something,
Cut, the meter's accurate again.
Yeah.
Yeah. Literally, yeah.
yeah. Well, you gotta think about when it was made, that was probably the cheapest thing that they could put
It
in
was
there,
cheap.
right?
That
Right,
was- But literally, they stuffed them in the case of the meter. I
Yeah.
think that was kind of.
yeah, yeah,
Just a comment for maybe the elders here in the group, Al, Rich. That wasn't meant as a dig, okay? The meters was how we do that.
You're older than me.
Yeah. I have several books on the subject.
Yeah.
Westinghouse meter repair
Okay.
manual,
Yeah.
panel meters. There's also several books on the subject that were over in England.
okay,
I got them from my professor who was deceased, and his wife said, come on in, take a look at his library. And
Yeah.
it was chock full of this sort of stuff.
wow,
So I have a lot of that I thought I could at least put down the name and the author,
yeah, mm-hmm,
maybe put it up on the web somewhere where if you are to spot them, these are hard to come by.
sure,
But if you do find them,
Yeah.
they're a gold mine of that sort.
yeah, that nobody just has that information anymore, so, yeah,
Question.
yeah,
On some meters, I've seen designation torch band movement. It looks like
Yeah.
it's on the law.
yeah,
Yes, it's torch band.
yeah, so
Enlighten me?
I've seen that too, and it has to do with the springs,
Okay.
okay, and how those springs interact with the suspension mechanism, but I don't really know the definition of what, I know it's more robust, someone might know better.
Spiral springs,
Yeah,
they have a straight band
okay,
that's pulled.
okay, a taut band,
Meters going this way, like
Yeah.
the picture. The
Okay.
band goes this way and it's pulled.
Okay.
And it actually twists.
okay, so it's almost like a torsion
Yeah.
type of a thing, okay, all right. I wonder if that has a bit more of a mechanical dampening than these little coil spiral springs.
I've seen them better meters.
Yeah,
Supposedly from
They
some
have no, so they don't have stick slip problem. So
Okay.
one of the things that kills these meters, you have a bearing there.
yeah, all right.
So you can get,
Okay.
that's what makes them
So the
stick.
taut band is the suspension and the resistance,
Yeah,
okay,
right.
okay,
So that's their spring.
All right.
It's their separate.
Okay. Okay.
Those stick slip, that's.
well, great, I learned something too.
Simpson manuals claim
Yeah.
that when they came out, because the taut band is, I think, was a Simpson thing.
Okay,
Well,
I had a
they-
triplet with that.
in
Triplet,
their
yeah.
book, they claim it is, but
yeah,
supposedly that was considered superior for field meters because if you move it, lay it, stand it, it was
They-
supposedly an improvement
Okay.
for field.
well, that little 310C you've got in your pocket up there, is that a taut band? So your little triplet 310 that you've got there, is that a taut band meter?
Yeah.
So,
Pass it up.
well, I gotta get my glasses out if I wanna read it, so I wonder if it says taut band on it, so. But these are, have you ever seen these little triplet 310s? These are great little meters, they're really great little meters.
I know a few years ago it's still made.
Yeah, this says, well, it says type 3 suspension, but it doesn't say taut band specifically on it, but I've actually got one of these that actually says Bell system right on the front, right on the label, and the voltage scales are different than the standard 310. So the Bell system must have said, we need these meters, all our techs want to have them, but we don't want a 3-volt scale, we want a 10-volt scale or something like that for the things that they need to measure out in the field. So it's kind of interesting. These are great little meters if you ever see them.
I worked for IBM, and those are the meters we got way back when.
Yeah.
And it said IBM on it. And
Yes.
IBM had their own voltages on it.
There you go. So
Like,
just like the Bell
60
system
volts,
had.
like
Okay.
60 volts.
Yeah, the Bell system had ones like that too.
What
So
they did, they had a contract both the triplet and with Simpson.
okay.
Simpson 260, I had the triplet,
Yeah.
and they gave it the, I think it was a KS 14611.
Okay.
Is the KS number.
Yeah.
And what happened was, I was working
I'll
on
pass
this
that back
once, and how the Bell system worked, if you put this meter,
Yeah.
this is a KS 14611 L1.
Yeah.
This one.
Okay.
You want the probes? same number, list 2.
Okay.
In the case, same number, list 3. So when to order 3 sets of leads, we by mistake we got 3 meters.
Oops.
One thing about this meter though is that we work on radios.
Yeah.
And the audio amplifiers, the grids, today, sometimes it's 4.7 or 10.
Okay.
You got a 20K or 30K per volt meter, you try to measure that grid voltage.
Yeah.
You're not only gonna not measure, you're gonna shut
You're gonna pull it, yeah.
Totally.
Yeah.
Turns the two.
Yeah, this is where, like I said, a VTVM or even a modern DMM has got a 10 megabit impedance.
I was in broadcasting,
Yeah.
and back in the 70s, we still had to do meter readings for the transmitter. They needed the plate voltage, the plate current, and the antenna current every 3 hours.
Okay.
A lot. The FCC had to do that.
Okay.
They wanted a 2/3 scale on all meters. In other words, if your plate current was 2.5 amps,
Right.
you had to have a 3 amp.
A 3 amp scale, yeah.
If you had a 5 amp meter in there, it was illegal.
Yeah. Yeah, that's for that reason alone, where we talked about full scale accuracy, because that carries all the way down.
They wanted it 2/3.
Yeah.
And the problem is, in one case, I had a dual power operation.
Okay.
And the RF thermocouple meter was, the normal current at one power was 3.29 amps. We had a 4.5 amp meter.
Okay.
But when I dropped to a different power, it went to 1 amp. I had to get
A different meter.
We had to put shunt switches across them and switch the meters in and out.
Oh, wow, okay.
To measure for the one power level or the other.
Right.
Each meter had to be 2/3 scale.
Right. Well, I said it makes sense for an accuracy standpoint, is why they did that.
Exactly.
Yeah.
That wasn't doing the FCC regulations in those days.
Yeah.
That's when they cared.
Yeah, and it's funny because sometimes specs like that will carry. Like even if they're out there with a digital meter now, the digital meter doesn't matter, right? But they'll still say, well, if I'm on a 5-volt scale in the digital meter, I got to be 2/3 of that. It doesn't really matter so much anymore. But it's funny how those specs stick sometimes, you know.
Well, on the meters, a couple of the meters I have, when you put it on the closer scale to what you're doing, you get more decibels.
Yeah, right. But it's funny because I remember reading a story many years ago in one of the trade magazines, and it talked about during World War II, ramping up production on fighter jets and things like that, there was actually a shortage of the leather that they were using for the airplane seats in the fighters. And couldn't figure out why is there a shortage of leather? I mean, it shouldn't be a shortage of leather. So someone looked into, well, the leather specification for the airplane seats said that the leather had to be treated with llama dung. Okay, so this is why if you go through eastern Pennsylvania and New Jersey, there was a lot of old llama farms. That's why they were there. There were llama farms to create the dung, to treat the leather, to create the leather for the spec for the airplane seats. So nobody ever looked into why there was the spec for llama dung to treat the leather. Maybe it's to make it last longer, make it softer, who knows. Someone finally looked into it years later, and it turns out that the spec that they got for the airplane leather came from the British Royal Mounted Army spec for saddle leather. And they used to treat the saddle leather with llama dung so the smell wouldn't spook the horses. But nobody ever checked why that spec was there, and they just carried that spec over to the airplane seat. But like I said, those kind of specs just carry along, and nobody looks into why they were there. So.
Not too many horses riding planes.
Right. So, any other questions? Good. Thank you very much.
And, I hope you don't mind if we tap you as a resource again.
Absolutely. Well, part of something that happened this year became named for the Northern New Jersey section of the ARRL Field Organization. I'm the technical coordinator. Okay. So part of my job is to do stuff like this in that role. So I'd be happy to come back.
Very good.
All right.
I do appreciate that.
So we're all sending off the meetings?
It seems like all the meters were for sale. It's the FS behind it.
Fullscale.
Fullscale.
But they were for sale. Don't worry, our next swap meet, we'll see plenty of them. But the price will probably go up now.
Yeah, now they're worth more. I didn't know how to use them. So I guess everything collected up in the corner up there?
I only have seats.
They're all up over there. Okay, so we'll collect them. Okay. All right, thank you, everybody.
Thank you. Just a reminder, next month we will be, September 8th, we will be at InfoAge. And presentation will be by our own Charles Blandy.
Okay, and you'll see it on the website very, very soon. All right, safe home, thanks for coming. And again, thank you, Professor Mike, for finding us this venue in lieu of not being able to go to home. Appreciate it. Pick up whatever you brought in, take it out, we have trash, and get rid of it. Did you know about the punch?